Hey, I'm Andre, also known as AP-AAiS. I'm the owner of this channel, and I would like to welcome you to this part 2 of the second installation of the German Kid Does Something having to do with Game Boy, the Raspberry Pi Pico and MIDI series, where we now explore different methodologies for which we can achieve 16-channel MIDI playback on the Nintendo Game Boy. Now, I say this is part 2 of a 3-part series, but really, this episode is standalone. You don't need to have watched the previous part to understand the full context of this video, since I'm now going to summarize all relevant information anyway. To recap, last year I created this little thing, which is the MAPico Boy MIDI interface, essentially a cost-reduced and cut-down version of the Arduino Boy MIDI interface by Timothy Lamb. In combination with a Game Boy handheld and a Game Boy software called MGB, MAPico Boy allows you to turn your Game Boy into a MIDI synthesizer, meaning that you can connect MIDI devices to it and then play music through the Game Boy sound generators. Now, already in the video which introduced MAPico Boy, I mentioned several pretty severe issues which hamper the music creation capabilities of both this new interface as well as the original Arduino Boy. The biggest issues of these by far is the fact that the Game Boy's APU, its audio processing unit, only mounts within itself 4 different sound wave generators. This means that even at the best of times, you can only ever play 4 notes on a single Game Boy at the same time, which is kind of an issue if you consider that the MIDI standard is actually built upon 16 unique MIDI channels, and that MIDI songs should therefore have the capabilities of playing up to 16 notes at the same time. Really, there is no way for us to overcome this limitation either. The only pathway that exists, which lets us play more than 4 different Game Boy sound channels at the same time synchronously, is by connecting up several Game Boy devices to a single MIDI interface source. That is exactly what my master's degree was about, which explored different methodologies of hooking up several Game Boys to achieve the playback of up to 16 MIDI channels. Now, at the onset, you might think that this is an unreasonably easy topic to choose for a master's degree. After all, we have the GameLink protocol available to us, and through that protocol, we can easily connect 4 or more Game Boys up to each other. So, if we then connect that network of Game Boys with a single MIDI interface, really, that should be that, right? Well, I'm afraid it's not quite that simple. There are several complications, especially having to do with MGB, which I'll explain to you now and which might make you understand why the topic of the creation of the single interface link system, which this video will deal with, was more than a bit difficult. To play back 16-channel MIDI signals across 4 interconnected Game Boy systems, we would essentially like to simply connect all these handhelds to our MIDI interface in just the same way we could previously connect just a single device. However, the Game Boy synthesizer software MGB, which translates the received MIDI signals into instructions for the sound generators of the Game Boy's audio processing unit, presents us with a pretty big limitation. As was previously stated, MGB, unlike the MIDI 1.0 standard, which is built to work with up to 16 simultaneous sound generators addressed by 16 unique MIDI channels, only uses the MIDI channels 1 through 5 with the hexadecimal address nibbles OXO to OX4, where channel 1, OXO, is received by the first pulse wave generator PU1, channel 2, OX1, is received by the second pulse wave generator PU2, channel 3, OX2, is received by the arbitrary wave generator VAF, channel 4, OX3, is received by the noise generator noise, and channel 5, OX4, is used as a poly mode. The first signal is received by PU1, the second by PU2, the third by VAF, the fourth by PU1, and so on. Because of this functionality at the side of MGB, we can only simultaneously play 4 different MIDI channels on the side of our Game Boy, even despite the fact that my Pico Boy actually sends out all 16 MIDI channels. Additionally, whenever you're using the channels 1 through 4, you should ideally avoid using channel 5 entirely, since it will otherwise cut off the dedicated generator signals for PU1, PU2, and VAF. This restriction complicates things massively. If we were to connect all Game Boys to a single GameLink cable that would carry the messages of all 16 MIDI channels, each Game Boy would only ever play the same notes of the channels 1 through 5 at precisely the same time. Therefore, simply connecting additional Game Boys to our interface wouldn't grant us any new musical capabilities. To combat this issue, we're left with 2 possible approaches. In my previous video, we designed the multi-interface link system, which isolated the electrical signals of each Game Boy and translated all MIDI signals with an address value greater than OX3 back into the range of OXO to OX3. Our Raspberry Pi Pico took care of both this channel translation process and also made sure that the translated signals were only sent out via the GameLink cable, which was specifically reserved for the one Game Boy we wanted to hear play the corresponding note. While this approach worked in both theory and practice, the additional wiring work made it extremely cumbersome to set up, and the necessity of recompiling the Raspberry Pi Pico control program whenever you wanted to change the channel assignments further hampered its usability. In an effort to hopefully allay these issues, I went on to design an alternative approach to the multi-interface link system. This new methodology was given the name Single Interface Link, and as you might imagine, it does away with the isolated electrical signals and allows each Game Boy to receive its data from a single interface connection. However, with each Game Boy receiving the data of all 16 channels within a MIDI song, I obviously needed to introduce a way for the Game Boy to autonomously decide if a received signal is to be processed by one of its sound generators or not. Such additional functionality obviously required me to perform some rather fundamental code changes within MGB. In the end, my work on MGB resulted in a new modification of the synthesizer software, for which each Game Boy sound generator can now be assigned a single MIDI channel that it will monitor henceforth. In the first section of this video, I'd like to detail some of the inner workings, as well as the practical usage applications of this modification which, in tune with my previous expansion on my MIDI interface control software called my Pico Boy Typhon, eventually received the name MGB Hydra. Before I begin detailing the new additions to MGB Hydra's functionality, let's first take a quick look at the original version of MGB, as it was built by its creator Timothy Lamb for use with the Arduino Boy MIDI interface. In this image, you can see the UI of MGB. Each of the 4 Game Boy sound generators is given its own column, while the different rows represent separate generator control settings that you can alter either through the UI or by using the appropriate MIDI CC signals. Without any modification, the generator of the leftmost column, PU1, receives all MIDI signals with the address nibble of OXO. The generator of the second column, PU2, meanwhile receives all MIDI signals with an address nibble of OX1, the VAF generator of the third column all MIDI signals with an address nibble of OX2, and the noise generator of the fourth column receives all MIDI signals with an address nibble of OX3. To change this default behavior via the program's UI, we would obviously like to add another row of control settings that allow us to change these channel mappings for each generator dynamically during the playback of a MIDI file. Adding such functionality, however, obviously requires a rather in-depth expansion to the previous interface code. At this point, I'd like to give my heartfelt thanks to the GitHub user Tim Stirrett for his amazing work on both the Arduino Boy and MGB projects. Tim has been spending his last few years updating both projects to newer SDKs while fixing some bugs and expanding the features of the original programs as he went along. Since Tim has been doing so much good work for Timothy Lamb's projects, I've also decided to base MGB Hydra on his MGB TS mod fork, and I cannot state enough how much easier his work has made my implementation of the following changes. Specifically, in the case of MGB, Tim fixed a couple of well-documented bugs of the original synthesizer and also translated large parts of the original assembly code back into the programming language C, which both made understanding the software's inner workings almost trivial and also simplified the implementation of the following changes by a fair bit. Really, in terms of coding changes, there's not even too much for me to talk about. I could certainly talk your ear off about a large number of minuscule changes which were required just to add 4 new variables to MGB, but I won't bore you with anything more than a short summary. Essentially, all of MGB Hydra's new functionality works through the addition of 4 new parameters to the internal dataset array, which contains the value defines for the numerous settings of each APU sound generator. After adding these 4 new parameters, one for each generator channel assignment, most of my following expansion work was centered around the update MIDI buffer function. Here, I added a new check of the status byte address of a MIDI message. Should the address of this byte correspond to one of the 4 values of the dataset channel assignment parameters, then the address of the status byte will be changed to the address that corresponds to the appropriate generator as per the default MGB MIDI standard. Should the status byte address not be contained in the dataset parameters, then we can simply leave this function, since our Game Boy isn't set to deal with this specific channel. In addition to this address check, I've also expanded a part of the subsequently called assembly code that defines how different MIDI CC types behave across the 4 generators of our Game Boy. Thanks to a few new assembly functions, MGB now supports one additional MIDI CC signal which uses the officially undefined address byte value of OX09. This new CC type works as a generator channel remap message within MGB Hydra. The address of the status byte determines the generator whose channel mapping is to be changed, while the value byte assigns it a new MIDI channel to monitor moving forward. For example, if we were to send out a generator channel remap message with the hexadecimal byte values of OXBO, OX09, OX01, then they will be interpreted as follows. OXBO indicates that we're dealing with a CC message for the sound generator that is currently listening to MIDI channel 1. OX09 indicates that the CC message is a generator channel remap message, and OX01 indicates that the addressed sound generator will now listen to MIDI channel 2 instead. So, through this new CC message type, we've already given MGB Hydra a first way through which the generator channel mappings can dynamically be changed during the playback of a MIDI song. However, for those of you who don't want to rely on MIDI CC signals to change these assignments, I've also expanded the MGB Hydra UI to both display the generator channel mappings and for you to change these mappings as you would any other generator setting. Here's a screenshot of the new MGB UI. As you can see, there's a new row of settings that indicate the channel that a Game Boy sound generator is presently listening to. Each generator can be set to listen to a MIDI channel in the range of 0, aka MIDI channel 1, to F, aka MIDI channel 16. At startup, MGB Hydra will load the generator channel mappings that are saved in preset 0. By default, these are the usual MGB channel assignments of MIDI channel 1 for PU1, 2 for PU2, 3 for VAF, and 4 for noise. But if you change these channel mappings and then save them into preset 0, you can dynamically adjust these defaults to your own needs. And with that, we've already discussed all the most important additions of MGB Hydra. In the next section, we can now look at how you can use the new potential these channel mappings offer us when it comes to 16-channel MIDI playback on the Game Boy. So, now that we know how MGB Hydra assigns the different MIDI channels to its sound generators, let's get into using these new capabilities for your own MIDI interface setup. Now, first of all, it's pretty important for you to know which MIDI interface you're using. Should you happen to own and use any version of my MAPicoBoy MIDI interface, whether it's been bought from my eBay shop or built by yourself, you're pretty much good to go. However, if you're using an older Arduino Boy interface, you'll have to change out the control software of the Arduino Boy with the software of a new Arduino Boy fork that I've named Arduino Boy Unleashed. This new software is required, since the original Arduino Boy code only sends out the MIDI signals that belong to one of the 4 MIDI channels that the APU generators of MGB have been assigned to with the max editor. Without any changes to this behavior, all other signals are simply ignored. With Arduino Boy Unleashed, however, Arduino Boy will send out the signals of all 16 channels regardless of any max editor assignments. Accordingly, you can attach additional GameLink cables to the output pins of the Arduino Boy and then connect more Game Boys running MGB Hydra to those, and you're now able to play up to 16 MIDI channels across 4 different Game Boys. With MAPicoBoy, the setup is similarly simple. The fully pre-built version of MAPicoBoy that's currently still on sale on my eBay shop is sent out with a GameLink cable that allows you to connect 2 Game Boys without further modification. Simply connect one Game Boy and one Game Boy Pocket, Light, Color, Advance or Advance SP to the original and Pocket connector of the fully unmodified side of the GameLink cable. Afterwards, you can simply run MGB Hydra on both Game Boys, set your preferred channel assignments for all 8 generators, and you're good to go. In this basic 8-channel use case, there's no modification of MAPicoBoy required whatsoever. Only if you'd like to use more than 2 Game Boys will you have to attach additional GameLink cables to the screw terminal. I highly recommend you check out the original MAPicoBoy build guide on my website, as it contains a concise explanation of how the necessary cable modifications need to be carried out. Once all your Game Boys are connected to the interface, you're pretty much ready to go. Afterwards, the setup of MAPicoBoy can be carried out as usual. If the program isn't yet loaded onto the Raspberry Pi Pico, you'll need to load the MAPicoBoy UF2 file onto the Raspberry Pi Pico. You can download it from its GitHub repository and load it onto the Pico by connecting it to the PC while holding down its boot cell button and then dragging the UF2 file onto the Raspberry Pi Pico storage device. For the rest of your usage time of the MAPicoBoy, you'll have to keep the Raspberry Pi Pico connected to a power source via its micro USB port. You'll know that it's correctly running the MAPicoBoy code when the green LED lights up. Additionally, you can press the boot start button of the Pico during playback to block MIDI CC signals from being sent out to the Game Boy. Unknown CC signals can oftentimes corrupt the memory of MGB, so it's best to keep CC signals blocked when playing back generic MIDI files. You'll know that CC signals are being blocked when the LED of the Raspberry Pi Pico flashes at regular intervals. Next, you'll have to connect the two MIDI plugs of the cable to your MIDI source with the MIDI terminals of the Pico Boy. Connect the MIDI out plug with the MIDI in terminal and the MIDI in plug with the MIDI out terminal. After that, you'll have to run one instance of MGB Hydra for a Game Boy or Game Boy Flash card on each Game Boy you would like to play sounds through. Now your single interface link system is ready for MIDI playback. Simply play a MIDI file or send out a MIDI signal from your MIDI source, and MGB Hydra will automatically do all the work so that each Game Boy only plays back the signals of the 4 MIDI channels that its generators have been assigned to. So that was that. As you can see, the actual effort of creating a single interface link system for 16-channel MIDI playback across several interconnected Game Boys actually turned out to be surprisingly manageable. More than that, the single interface link approach has also managed to improve on pretty much all shortcomings of the previous multi-interface link system. It's easier to build, it's easier to use, and it's now possible for you to dynamically switch the different channel generator assignments on the go. There's plenty of cool stuff you can do with the new capabilities of MGB Hydra, since it massively expands the MIDI capabilities of the Game Boy. If you're a retro composer or just interested in chip music played on real hardware, I bet that you can think of 1,000 cool things which were previously impossible to pull off with just 4 sound generators, but are now made conceivable for the power of 4 different Game Boys playing in perfect harmony. Of course, despite the single interface link methodology's greatly improved and novel potential, there is one major pain point that would be unfair for me not to mention: pricing. Since the playback of 16-channel MIDI songs requires you to not only own a MIDI interface, but also 4 Game Boys, as well as 4 flash cartridges with which to play MGB Hydra, you're most likely to pay well upwards of $200 to gather all the hardware that a 4 Game Boy single interface link network would require to function. Sadly, there's not much that we can do about this fact either. Since each Game Boy only has 4 sound generators, there's no way that we can simultaneously play 16 MIDI notes with fewer than 4 Game Boys. Similarly, since we need to run a piece of software to interpret and translate those MIDI signals on the GameLink port, there's also no way for us to avoid the cost of buying 4 flash cards. Really, the only point of attack for any cost reduction measures would therefore sit at the MIDI interface. After all, the only reason we need an Arduino Boy, Pico Boy, or any other interface in our system is to translate the MIDI signals of a MIDI source into the GameLink protocol. However, all of the Game Boys in our system obviously already speak the GameLink protocol language natively. So you might be asking yourself if we can't use one of the 4 Game Boys in our system as a MIDI source directly. If such an approach were to work out, then we could, at the very least, save ourselves the cost of a MIDI interface. This was the precise thought process that eventually led to the development of the third method of interconnected MIDI playback on the Nintendo Game Boy, called MIDI on the Game Boy. This entire topic turned out to be incredibly complex, led to the creation of 2 different software suites called MIDI Dumper GB and MIDI Boy, and will be covered in a third video later on. For now though, I'd like to simply thank you for watching this video though. If you want to learn more about the single interface link approach or about MGB Hydra, you can check out the GitHub repository, which I've linked in the description down below. Otherwise, if you want to learn more about my Pico Boy as well as my different approaches of achieving 16-channel MIDI playback on the Game Boy, you can watch the different parts of the series all on my YouTube channel here. Finally, if you want to get your own hands on a Pico Boy, you can do so at the eBay page also linked down below. However, be aware that I don't have too many more of these things left in stock, so it could very well be that by the time you watch this video, they're all sold out. With all that chilling out of the way though, I'd like to wish you a fun rest of your day and leave you with a final piece of music played on a single interface link network to play out this video. This is AP, signing out. Have a good one.